Hello everyone, welcome to the course Computer Networks. This is S. Parvathi, Assistant Professor, Department of CSIT, MLR Institute of Technology. In today's session, we are going to discussing about dynamic routing algorithms. In previous session, we already discussed about static routing algorithms. There, three static algorithms are there. Those are shortest path routing algorithm and next flooding, flow-based routing algorithm. These three already discussed in previous session. Now we are going to discussing dynamic routing algorithms. First, let us see the overview of today's session. See, in these dynamic routing algorithms is also called as adaptive routing algorithms. These adaptive routing algorithms are the distance vector routing algorithm, link state routing algorithms. These two called as the adaptive routing algorithms, that is dynamic routing algorithms. So, afterwards we discuss what are the differences between distance vector and link state routing algorithm. Let us see all these topics in today's session. First, what is distance vector routing algorithm? Distance vector, we are talking about the distance and vector. That is distance vector routing algorithm. First, before going to discussing this distance vector routing algorithm, we have to know these three keys. What are the three keys? What is distance metric is there? What is the routing table? And next, what is Bell-Munford algorithm? Before going to this algorithm, we have to know about the distance metric, routing table and Bell-Munford algorithm. First, what is distance metric? Distance metric is nothing but to find the best route to a destination. Suppose if you want to travel from the source to destination, from A to C we have to travel. So, we have to find the best route to travel the distance. That is the distance metric. So, this distance vector routing algorithm employs the distance metric, talking about the best route. So, it is talking about mainly the number of hops. How many hops are there between? Suppose if you want to travel from A to D, this is the source, this is the destination, this is the source, this is the destination. So, from this source to destination, if you want to travel, suppose this is the one route, this is another route. Traveling this particular source to destination. So, in that particular case, from these two, these are the routes. So, with this A to D is one route is there, A to B, B to D is one route is there, A to C, C to E, E to D, one more route is there. Here three routes are there to go from source to destination. In that we are going to take the best route. Which one is the best route? How we are going to take based on the number of hops. How many hops are there between from source to destination. And the next condition is bandwidth. And next one is the latency. Bandwidth is talking about the distance. Means between the two, how much exactly at what time we are sending the data. What is the capacity? Means speed. It is talking about the speed. What is the speed for sending the data? And latency is talking about the maximum transfer rate. Means it is talking about the how many number of hops are there. That is the latency. These are some examples of the distance metrics. And next one is the routing table. What is routing table? It is having, means if you want to go through this distance vector routing algorithm, we have to know about the routing table. Routing table, exactly what it will tell. It will says the every node is maintained the routing table. It is containing which includes the details on the most efficient route. Means from source to destination, which one is the best route to taking that particular path to reach the destination. That is mainly having that routing table. So this for each and every router is having the routing table. Suppose this is the C router is having the routing table. Exactly, it is talking about the how to reach the destination. That is the first condition. And the next one is the next hop node. It also tells the which node is the next node. That is also included in the routing table. At the same time, what is the traveling time in between source to destination? That is also listed in the routing table. That is talking about the routing table. This routing table. So, nodes are communicated with the neighbors. What are the nodes are communicated with that particular router? Suppose if you want to talk with B. So, what are the neighboring nodes of this particular B is A and C. It is having the information about the which are neighbors to that particular router. If you are talking about the B, it is talking about the nearest neighbors to that particular node. That is the neighbors. So, whom they are connecting directly linked to update their routing table. Means to whom this B is connected for A and C. That is the routing table. It is mainly talking about the directly links to that particular router. And next one is the Bell-Munford algorithm. What is Bell-Munford algorithm? Means if you want to use this distance vector routing algorithm, we have to follow the Bell-Munford algorithm. It is saying that to determine the best route to the target node, Means mainly it is for what purpose we are going to use this Bellman code algorithm. It is talking about the selecting the best route among the all other routes. The distance vector routing employs the Bellman code algorithm. It is mainly employs the Bellman code algorithm until this process is going to be repeated, until the convergence is going to be achieved. Means to reach the final destination. What is the final result here? To find out the best route for all routers. We have to find the best route for all routers. Whatever routers are there in that particular network, for all routers, it will select the best route. Convergence is achieved is nothing but for selecting the best route for all routers. The algorithm iteratively updates the distance to each network node. Means whenever it is changing, means whenever it is talking about the routing table, automatically, iteratively, it will update that particular routing table. So this is about the Bellman-Ford algorithm. These three keys we are involving in the distance vector routing. So next, this distance vector routing, what is exactly how it is going to be work? So it is known as the Bellman-Ford routing algorithm, and it is also called as the Ford-Fulkerson algorithm. These two names are also considered as a distance vector routing algorithm. So it is the original ARPANET routing algorithm. What is ARPANET? Advanced Research Project Agency Network. It is nothing but Advanced Research Project Agency Network. This is the original ARPANET routing algorithm. So this distance vector routing algorithm mainly talking about it can be operated by having each router maintain the routing table. Means what are the routers are involved in this particular network. So this is the network. Here how many routers are going to be involved? Total R1, R2, R3, R4, R5. Total 5 routers are there. So for each and every router, it has to create the routing table. It has to maintain the routing table. For what purpose we are using this routing table? For giving the best known distance to each destination. We are going to use the routing table. That is distance vector routing. Here what is distance, what is vector? Distance is talking about the metric. It is like number of hops. How many number of hops to reach that particular destination between the routers, between the source to destination. Suppose if I want to reach from R1 to R5. So how many number of hops it is going to be traveled? Suppose if we choose the route R1, R2, R3, R5. If we choose this route, here it will travel 3 hops. And coming to this route R1, R4, R5, only 2 hops are going to be there. That is the distance. What is the distance exactly? To travel from source to destination. So next one is the vector. Vector is talking about the direction. In which direction he has to follow. What is the next router? Which one is having the best distance? That is the which direction he has to follow. That is the vector. That is distance vector. It can be used the RIP. RIP is nothing but routing information protocol. This protocol is used in the distance vector routing algorithm. So it is mainly follows which algorithm? Bellman-Ford algorithm. That concept is going to be used mainly for calculating the distance. For calculating the distance means for selecting the best route among the all routes, we are going to use the Bellman-Ford algorithm. How it is going to be works? We have to see how the working is going to be happen. First, what it has to know? First, each router knows its neighbors. Suppose here the routers are R1 is there, R2, R3, R4 and R5. 5 routers are there. Here, first each and every router knows its neighbors. Suppose if R1 is there, what are the neighbors of R1? That is R2 and R4. These are the two neighbors. What are the neighbors is nothing but the direct link. Directly linked with that particular router is nothing but the neighbors. So here the neighbors of R1 is R2 and R4. These are the neighbors. And next step is router share their routing tables with the neighbors. Means what exactly we said? Here the first it has know the neighbors. At the same time it contains each and every router we already discussed, right? Each and every router maintain the routing table. Every router is having the routing table, their own routing table. So these routers share these routing tables to these neighbors. That is the second condition. So these tables are updated by exchanging the information with the neighbors. These whatever tables the routers are created, that can be changed automatically whenever it is whenever it is going to be communicated with the other neighbors, means other routers, it is going to be updated automatically. Means whenever it is found the shortest distance, it is going to be updated. That is the condition. And routers replace the routers. How it is going to be replaced? Their own routing tables anytime. Anytime it can be replaced. Whenever it is finding the best route, automatically it will change. Suppose from R1 to R5. Suppose this is the best means this is the condition. We are based on the cost. We are going to find the cost, find the best distance, right? That's why here is 8, here is 8, here is 7. This is the distance. We will assume that. So suppose from R1 to R5 if you want to travel. So 8 plus 7 is what? Total is 23. So suppose from this R1 to R5 if you want to travel, here it is going to be 5, it is going to be suppose 10. Total distance is how much? 5 plus 10. That is the 15 only. Means what it will think? Suppose previously the case maybe this is the shortest route. After finding best route, this is the best route, right? 5 plus 10. So it is going to be updated. Whenever it is finding the best route, automatically it is going to be updated. Means the routing tables are going to be updated anytime whenever it is finding the best route. That is the condition. So updating whenever it is find the best route, automatically it will update the routing table. So this process is going to be continued as it is. It is going to be repeats all routers having the shortest path to each and every node. Means each and every node from R1 to R2, which one is the best node? From R1 to R3, which one is the shortest path? From R1 to R4, which one is the shortest path? From R1 to R5, which one is the shortest path? Like that, from one router to R1 to, it will check to the all other routers from R1 to R2, R3, R4, R5, which one is the best path? Based on that routing table only, it will going to be continue this process until it will reach to the best destination between R1 to R2, R1, 3, R3, like that. For each and every router, we have to calculate. That is the process of distance vector routing. So this distance vector routing, see how it is going to be work. We will see. See here. So in this, we will see one example. Here the routers are A, B, C, D, E. Total, how many routers are there? 5 routers. A is here, B is here, C, D, E. Total 5 routers are there. In these 5 routers, each one is, we are mentioning the distances 5, 4, 6, 7, 3, like that. We mentioned the distance also. So first what we have to do? First initially we have to find the distance table. This is the first one. What we have to do? For each and every router, we have to construct the routing table, right? That is the first condition. What are the nearest neighbors of the A who are directly connected to the A? Only E is going to be connected. For E, who are the nearest neighbors to the E? E to A, E to B is there, E to D is there. Means 3 neighbors are there. For E, the neighbors are A, B and D. And coming to B, what are the neighbors of the B? That is E and C. And the next one, and coming to the C, what are the neighbors of C is D and B. Like that, here are the neighbors. These are the direct link, means communication between the neighbors. So, first we have to find the routing table. Means each and every router maintains the routing table. For each router, we are going to find the routing table. That is the first condition. We know already who are the neighbors for that particular router. So, next we have to construct the routing table. So, how to construct the routing table? For router A, we are going to find the routing table. How we are going to find the routing table? For that, we have to mention that what is the destination. Next one is the means from A to B. Means for every router, we have to find the shortest path to all other nodes. That is the condition. Means from A to B, what is the shortest distance? A to C, A to D, A to E. From A, from source, this is the source, to all other routers, we are finding the shortest distance. So here, this is the router A table. Here we are talking about the destination is from A to A, what is the distance? From A to B, from A to C, A to D, A to A, we are going to find. So the first one is the from A table onwards. A to A, what is the distance? From A to A, the first condition is A to A, means A to A only, that table only, self table. So here the distance is 0, there is no distance. The hop is, what is the next hop? It is going the A only, right? A to A, there is no distance. So next hop is A only. And coming to next one, A to B. Next we are talking about A to B. If you want to travel to A to B, there is no direct link. So for the first step, we have to talking about only direct connection. There is no link. So we have to write the distance is infinity. We don't know the exact distance between A to B. So here the infinity, we don't know. So and the next one is the what is the hop A to B? Means here there is no direct link. So it will give as it is empty. And the next condition, A to C, we are going to find. A to C is nothing but A to C also, there is no direct communication is there. There is no direct link. So we have to write this distance also infinity. And next one, Here the next hop is also not there. So it is give empty. And the next one is the A to D we are going to find. A to D is nothing but what? A to D is talking about A to D also there is no direct communication. So here also the distance is empty, that is infinity. So here the next hop A to D there is no direct link. So it will also give the, what it will give? It will give empty. There is no next hop. And the next E, A to E. Next one is A to E. A to E the connection is there. So what we have to write from A to E? We have to write. So here A to E, the distance is, what is the distance here? Here it is 5. We are writing the 5. What is the next hop it will going to be reached? That is the A to E. The next hop is E. We are writing here is E. This is the A table. At the same time we have to find for each and every router, we have to find the router tables, routing tables. So this is only for router A table. Suppose the next case here, suppose if you find for the router E table, we are finding the table for E. So for E also we have to find for E to A distance, E to B distance, E to C, E to D, E to E also we have to find. That is the case. Suppose that is A, B, C, D, E we are going to find. For E to A means the destination is A. From E to B, E to C, E to D and E to E. This is the condition. For each and every router we are going to find the distance. So the distance from E to A. E to A the connection is there. That is E to A. Here is the connection. So what is that connection? 5, right? So that's why we are writing 5 here. At the same time E to A, where it is going to be reached? The next hop is A only, right? This is the hop is nothing but the next hop. Which hop it is going to reach? Means it is going to be reached to A. This is the, this one is over. And the next condition is E to B. E to B is talking about what exactly? E to B is talking about E to B, the distance is, here the link is there, here it is going to be 4. E to B is 4. This is the 4. And the next hop is what? B. Here is B. And E, from E to C, there is no direct communication. Here is, there is no communication. So that it is, we don't know this distance. That's why we are giving this as infinity. And next, there is no next hop. That's why we are giving empty. And from E to D, we are going to talking now. So E to D, here the connection is there. The link is 7. The distance is 7. So here the next hop is what? E to D it is going. So the next hop is D. And next E to E means here is same. E to E is nothing but the self. There is no distance. So it is 0. E to E only it is going. So it is E to E only. That is the condition. This is the router table for E. Routing table of E. Suppose if we found that routing table for B. So here is the destination. Here is the distance. And here is the next hop. So from B to A, B to B, B to C, B to D, B to E we are going to find. Means here total how many routers are there? 5. That's why we are taking total all routers. From B to all the routers we are finding the shortest path. That is the condition of the routing table. So B to A, what is the distance here? There is no direct communication. So there is no distance. That is infinity. We don't know the distance. And next hop is also empty. That is B to A. And B to B. B to B means what? B to B means self only. B to B is 0. The next hop is only B. And the B to C the communication is there. So here B to C is the distance is 6 and is going to the next hop is C only. And next B to D. If we are talking about B to D, there is no communication. There is no direct link. So here B to D is infinity and this one hop is empty. And B to E, here the distance is there. B to E how much is there? 4 is there. B to E 4 is there. And the next one, next hop is what? B to E, E only. Like that we have to find this is the B table, B routing table. Like here is A table, here is E table, here is a B table. Like that we have to find for A is completed, B is completed, E is completed. We have to find for the C and D also. This is the first condition. And next step, what we have to do? See, next what we have to do? So suppose the next step is step 2, update the table node A. How we are going to update? So till here we found what we found? A table, E table and B table we have seen already, right? So next, what is the neighbor node of this particular A is E. Through these neighbor nodes, where we have to go? Means we are finding the shortest distance. So that is we are going to updating. So here also destination is there, Means from A to A, A to B, A to C, A to D, A to E. And then what is the distance from A to A to B, A to B? And what is the next hop? What is the pair from to reach this particular destination? Means in previous case we don't know some distances, right? Like infinity we have given. That we are going to identify which one is the shortest path for reaching A to B, A to C we have to find. That is the condition. So here see how we are going to find based on these neighboring nodes of that particular router. So here node A we are going to find. So from A to A it is 0 only. The next hop is A. Here there is no pairing. That is empty. And the next case is A to B. It is talking about A to B. What is the A to B? The distance here is direct link is not there. But the link is how the link is going to be there. A to E already we have given. That is A to E already we mentioned here. A to E is 5 distance is there. From E to we can reach the B, right? So that's why we are writing the total distance 5 plus 4 is 9. A to B, A to E, A to E to B we are going to travel. So 5 plus 4 is 9. That is we have to mention 9. And the hop is here. Means the next hop for reaching A to B is the next hop is what? E only. So here we have to write E. And next what is the pair to reach from A to B? So A to E we have to travel, E to B we have to travel. Like that we have to give the shortest path from A to B. And next one is A to C. A to C, the direct link is not there. But the neighboring node is only E. That E is also not connected to C. That's why we are writing here it is infinity. Means we don't know till now also. After reaching to E also we don't know the connection from A to C. That's why we are writing here is infinity. And next here the next hop is empty. So A to E, E to C we checked. E to C we checked actually. Because A is the neighboring node of A. That's why E is the neighboring node of A. That's why we checked the node. But E to C also there is no connection. So it is giving us infinity. And next case is A to D. A to D is A to D how we have to travel? A to E. E to D we have to travel. So suppose if we take that particular case, what is the total distance? 5 plus 7. That is 12. 5 plus 7 is 12. And it is going to be next hop. How we are traveling from A to D? The next hop is E only. So we are writing E. And the condition is A to E. E to D we have to travel. That is the pair. This is the A to D. And the next one is A to E already we know. That is the E is 5. The next hop is E only. That is the pair is A to E. This is the condition. Like this we have to update the routing table. For the same way this is only for node A. This case also we don't know this A to C. Again we have to find the next routing table for the next case. Means still here we connected to A to E, we connected B and D, right? Next case we from A to E, E to D, D to C or A to E, E to B, B to C we can find the distance from A to C, right? Like that again we have to find the step 3 also. In that step 3 we have to find the condition for routing table for A. Means for reaching A to C. At the same time that time also there may be modifications for these distances. There may be you can find the best route also. That time you can change these routes also. That is the condition. So suppose in this step 2, this is for A only. So if we found for E table. Here is also E we wrote, right? We found for E table. What is the changes we have to change? See. So here is destination is there. Here is distance is there. And the next case is what? Hop. And next pair is there. This is the step 2. So E to A we have to find, E to B, E to C, E to D, E to E we have to find. That is the case. So to this E table, see the distance E to A. What is the distance? 5 we know. And the hop is A only. And the pair is E to A. That is okay. E to B. If you find E to B, here the connection is there directly. E to B already there. That is 4. B only, E to B. And the next case is E to C. E to C is there is no connection directly. But we have to find the, already we know the neighboring nodes of E is B and D we know. Previously we already wrote that B and D are the neighboring nodes of the E. So in that particular case we found the distance for C. See, E to C is, suppose if you go for this route, 7 plus 3 is 10. Here also 4 plus 6 is also 10. We can, if both routes having the same cost, then we can choose any one from these two. Either you can go E to B, B to C, or you can go E to D, D to C, you can go. So here I am going to take any one. So suppose if I take the E to D, D to See, if I take, so what I have to write E to C? Suppose here the distance is 10. The next hop is you have to write, if you select this particular route, E to D, D to C, then you have to write what is the distance here. Here the distance is what? Here the distance is total 7 and total is 10. Here the next hop is D, and here the what we have to write, E to D, D to C you have to write. E to next D you have to find. E to D already 7 is there. Here D only there. E to D. And E to E, that is 0 only. E to E, there is no pair. Like this you have to find the table for each and every router. This is the condition of the distance routing algorithm. So like this you have to find for every router. Similarly, update the step for all nodes in the model. At the end of the updated step, you will get the most efficient routing data. Finally, if you find like this for all other routers, for A, for B, C, D, E, for all routers, you have to do calculation for all the routers. Like this, you have to do the routing table. Finally, you will reach the best path for each and every router from that particular router. That is the main condition in the distance vector routing algorithm. See, this is about the example of the distance router algorithm. So, what is the main drawback of this particular algorithm? So, using this particular distance vector routing algorithm, the main problem is counter to infinity problem. What is the counter to infinity problem in this particular case? Suppose we are traveling through one router to another router, right? Here A, B, C, D, E are the routers. Suppose first only A router is only there. A is only there. The first case is what? A is only there. It is starting at what condition here is 0. Means here before A any routers are there? No one is there. So here is 0. Suppose B is came. What is B is saying? B is I am writing 1. How I am writing 1 means before B how many routers are there? One router is there. So I am writing 1. So this is the first case. And afterwards C is coming. See here C is there. So after B C is coming. So here I am writing C. Before C, it is what C, if you write C, what C will assume? Before C, 2 routers are there. That is the meaning. So next case, that is D is coming. If D is coming, D router is coming. If I write 3, how I am writing 3? So before D, how many routers are there? 1, 2, 3. So here we have to write the 3. Like that. And suppose if you write E, E is there. Suppose E, what we have to write? Before E, how many routers are? 3. 3 is there. 3 plus 1. How many are there total? 4. Means E. Before E, how many routers are there? 1, 2, 3, 4 routers are there. Here there is no problem. Like that it is going to be updated in distance vector routing algorithm. Here there is no problem. But what is counter to infinity problem? How it is going to be drawback of the distance vector routing algorithm? See now, this is the first section, second, third, fourth section. There is no counter to infinity problem. How exactly it is going to be happened in distance vector routing algorithm? Initially all are 1, 2, 3, 4. There is no problem. 0, 1, 2, 3, 4. That is okay. Here if it is going like this only, there is no problem. Suppose here the case is, suppose here it is going to be connected. Here I am writing 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. The first case is here is A, B, C, D, E. So suppose after some time, here is it is okay. After some time, A router is going to be failed because of some power loss, power failure. It is going to be getting down. This router is going to be getting down. So here it is not in working. So what B will assume? Exactly? So B is thinking that there is no A. Means what it is going down? It is giving updated from the C. What it is going to be updated? It is going to updated 2 is there. So I have to become to 3. Means 2 plus 1 is 3. Like B is going to be updated. So as it is 2, 3, 4 is going to be there. Main reason is here because of power failure, there is a chance of it is going to be assumed wrongly. That is the condition. And the next case is, suppose B is updated now to 3. So what C will think? So maybe B is my neighbor, but B value is what? 3. So after updating this particular value, if it is assumed 3, the neighbors, how many neighbors it is going to be updated? If it is 3, it is going to update it to 3 plus 1 is 4. It is going to update it to 3 and 4. So it is as it is. Means here it is going to be considered as wrong way. So at the same time, again here is 4. What it will think? So here this is 4. Here it is going, now it is updated now. So what it will think now? Now next is C. What it will think? It is 4 means my nearest neighbor is B. It is going to be updated again 5. It is 4. So at the same case here, D is going to, what D will think? Here is my E is my nearest neighbor. I am taking from E. That time what it will think? It will 5 and this is 4. At the next case, these two are updated now, right? These two updated. And the next case, so what C will think? So my nearest neighbor is B. Again, it will going to be updated to 6. Here is 5. Here is 6. At the same way, here also updated to, here is 5. Here is 6. This process is continually wrongly. It is going to be wrong way. At the same time, it is going to be infinity times. It is going to, the loop is going to be repeated. That is the counter to infinity problem. Exactly, counter to infinity problem. That is the condition. After 6th extent, this is the condition. Like this, it is going to be updated till infinity. So this is the counter to infinity problem. Because of power failure of one particular node, it is going to be updated wrong way. That is the condition. That is called as the counter to infinity problem. So the solution for this problem is linked state routing algorithm. To overcome this problem of distance vector routing, we are going to use the linked state routing algorithm. Let us see what is linked state routing algorithm. So, linked state routing algorithm. It is a linked state routing algorithm mainly talking about the 5 steps. It is having 5 steps. What are the 5 steps? So, first you have to discover the neighbors of that particular node and learn their network address. So, suppose this is the diagram. In this particular diagram, first suppose this is the source. From these stores, we have to send the packets to all other nodes. First, you have to discover its neighbors. What are the neighbors of this particular S? This is the source side. The neighbors of this particular S is A, B, C. Means who are directly linked to that particular router, that is called as the neighbor nodes. So here the source S neighbors are A, B, C are the neighbors. And after finding the neighbors, you have to learn their network addresses. How we are going to find the nearest neighbors? For sending the hello packets to that particular routers. Then you can find the nearest neighbors. Suppose, to understand this, suppose if I am new to the college, I am the new student to that particular college. So, whenever new student is coming, the class is new to that particular student. Whenever he is sitting some that particular place, he is going to talk with all other friends who are near to that particular place. How you are going to talking with that particular new student to all other students who are near to that particular place? Then he is saying hello to student who are near to his place. So he is saying hello. At the same time, that particular new student is also giving reply to this student. Like that, it is going to be happening. Means to discover the neighbors, we are going to give some hello condition. So here he is giving hello. Here he is giving hello. Like that, he is giving hello. Then he will give some reply to yes, hello. This is the condition to discover the neighbors. And after discovering the neighbor, you have to learn the network address. Network address is nothing but what exactly is talking. So, whenever we are saying hello, next what we are asking, what is your name, address, like that, right? That is we are knowing about the network address for sending the hello packets. For sending hello packets, we are going to know about the nearest neighbors and at the same day address. That is the first condition. And the next one is after hello packet sent, next one is measure the distance. You have to measure the distance. What is the distance between S to C, S to B, S to A? How we are going to find the distance? Using the echo packets. Using echo packets, we are going to find the distance. How we are going to find the distance? For sending, suppose if I send some information from S to C, that is A. We are sending information, that is A. Means the distance is A. From C to S also, the distance is there, right? For giving reply, that is B. The round trip time is nothing but for sending and receiving total. For finding that particular distance, that is A plus B. That is called as round trip time. And the next one is the estimated delay. Means for sending that particular packet to this particular source, we have to find the estimated delay is A plus B by 2. Means for sending is A, for receiving is B, the estimated delay is A plus B by 2. That is the condition. Like that, we have to measure the distance of this particular neighbors. And the next case is, after finding the distance, next one, construct the packet. You have to construct packet for each and every node. Whatever it has learned just previously what it has learned, for that it has to construct the packet that it is going to be tell about the distance of that particular node. That is the next case. And next one is send this packet. You have to send the packet and receive the packets from all other nodes. That is the next one. Whatever packet it is going to be constructed, that is going to send to all other nodes. That is the fourth one. And third one is compute the shortest path. Finally, what you have to do? Compute the shortest path to all other routers. That is the fifth case. Till here we understood. First you have to send the hello. Means to discover the neighbors, you have to send the hello for discovering the neighbors. And next case is what? You have to find the distance. Measuring the distance. How we are going to measuring the distance? Using the round trip time and estimated delay. That is a plus b by 2. Then okay. Next, how we are going to construct the packet? How we are going to construct the packet? That is the building the packet. How we are going to construct the packet? See here. This is the example. See this example. In this example, total this is how many routers are there? A, B, C, D, E, F. Total how many routers are there? 6 routers are there. Here the distance is there. A to B is 4, B to C is 2, C to D is 3, D to F is 7, E to F is 8, A to E is 5, and B to F is 6, and at the same time E to C is 1. Like that we have given some distances. So using these particular example, we are finding the building the packets. How we are going to construct the packet for each and every router. For each and every router, what we have to construct? You have to construct the packet. This is the packet. In link state algorithm, we can call it as a packets. In distance vector, we can call it as a routing table. Here we call it as a packet. Each packet is containing which for A we are constructing, that is A. First we have to write for which packet you have to construct. For A, this is for A, we are constructing the packet A, this is. So here first we have to write the which packet this is, that is A packet. Next we have to write the sequence and age. What is sequence packet and age packet? Sequence packet is talking about thing. Each packet contains a sequence number. What is the sequence number? And keep tracks how many times this packet has been sent. Exactly, sequence packet is saying about the sequence number. At the same time, it is saying about the how many times this packet is sent. That it is going to be sent. That is the sequence packet. Next one is age packet. What it is going to be tell? Age packet is talking about the life of the packet. What is the life of the packet in that particular network? That is talking about the age packet. After passing 1 by half, it is going to be decremented by 1. That is the age packet. Means each packet we are going to construct the packet table. So each packet we have to write the first packet. Next we have to write the sequence packet. It is having the sequence number and it is also talking about the how many times the packet is going to be sent. And the age is talking about the lifetime of the particular packet. And next we have to write the nearest neighbors through that particular packet. So A is my router. For A we are constructing first. What is the neighbors of this particular A is? B and E only. B and E. These are the neighbors. So B is totally it is having the distance is 4 and E is having the distance is 5. Like this we have to construct the packet for each and every table. This is the for A router we are writing. And suppose if we take B router. B neighbors are A is there, F is there, C is there. These are the neighbors. Say here A is there, C is there, F is there. We have write the distances for A to B to A is 4, B to C is 2 and B to F is 6. We have to write. Already we know this one sequence and age packet. And next one for C also we have to construct the packet. So sequence and age as it is for each and every packet, that is talking about the sequence number, the life of the packet. And next one, what are the neighbors of this particular C? C neighbors are B is the neighbor, at the same time D is the neighbor, at the same time E is the neighbor. B, D, E are the neighbors of C. So C to B is 2, C to B is 2, C to D is 3 and C to E is what? 1. That is the distance. Like this we have to construct the packet for each and every router. So for D we have to construct. For D it is going to be D. D links are C and F. C and F are the neighbors of F. So these are the C and F are the neighbors of D. So the distance from D to C is 3 only. That is 3 only. D to F is 7. Sequence and age packet as it is. And for E we have to construct. For E neighbors are A. Here is A is there. Here is C is there. Here is what? F is there. ACF are the neighbors of E. So we have to find the distance 518 distance of ACF. These are common sequence and age. For F also we have to find the packet, construct the packet. Sequence age is common. The neighbors of F neighbors are E is there, at the same time D is there, B is there, EDB is there. So B, B2, F to B is 6, F to D is 7, F to E is 8. Like this we have to construct the packet for each and every router. This is the third step. And see, this is the third step. Here till here we know only. We are constructed the packet. The next is what? Send this packet to all other nodes. So, see, next step is what? Next fourth one is what? Send this packet to all other routers. And next, compute this shortest path. Compute the shortest path. How we are going to find the shortest path? Using the Dijkstra's algorithm. Previously, we already knows the concept of Dijkstra's algorithm. Based on that only, we have to construct the shortest path to this all possible destinations. This algorithm only tells the router which link to use to reach the destination. What exactly it is going to tell? It is going to tell the how to go to the destination easily using the best path. This information is installed in the routing table. Whatever information is going to be there, that is going to be installed in the routing table. So, compared to distance vector routing algorithm, the link state routing algorithm requires more memory and computation. And compared to previous distance vector algorithm, it is having the more memory and computation. So, what are the protocols of link state routing algorithm? IS and OSPF, these two are the protocols of the link state protocol. So, IS is nothing but intermediate state, intermediate system. That is the intermediate system, that is IS. OSPF is nothing but open shortest path first. These two protocols we are going to use in link state algorithm. And coming to next one, what are the differences between distance vector and link state routing algorithm? So, distance vector routing is mainly talking about the local knowledge, and link state algorithm talking about the global knowledge. Means it updates the table based on the information from the neighbors. It has the knowledge about the entire network. Means here we are only talking about the nearest neighbor information we are taking. It is talking about the entire network. And it can be used, this distance vector routing, we are going to use the Bellman-Ford algorithm. And link state algorithm, we are going to use the distance and Dijkstra's algorithm. And coming to distance vector, the traffic is very less. And here the traffic in the link state, it is more. And the convergence is also here, it is going to be slowly. And here the convergence is going to be faster. And this distance vector routing faces the counter to infinity problem. Here in link state routing algorithm, there is no counter to infinity problem. The practical implementation is RIP and IGRP going to be used for distance vector routing algorithm. The practical implementation for these link state, we are going to use the OSPF and ISIS protocols for link state routing algorithm. These are the some differences between distance vector and link state routing algorithm. And coming to today's summary, today we discussed this dynamic routing algorithms. What are the dynamic routing algorithms? First one we discussed this distance vector routing algorithm, and next we discussed link state routing algorithm. And finally, we have seen the differences between distance vector and link state routing algorithm. These are considered as a dynamic routing algorithms. Thank you.